Before we start connecting the nodes, I want to explain the core concept for creating the Koch fractal. We begin with a single line segment defined by 2 points, where the red numbers 0 and 1 denote the index numbers of those points. Next, we divide the line segment into 4 equal parts, and this gives us 5 points with index numbers from 0 to 4, and pay attention to the value of the line's length. Next, we see 2 dashed lines positioned at 1/3 and 2/3 of the original line segment's length. On the segment below, we've defined 5 points, 0 to 4. Points 1 and 3 are the ones landing precisely at the 1/3 and 2/3 marks. This is the exact setup for our geometry nodes. Then, we move the point with index 2 upwards so that the 3.1, 2, and 3 form an equilateral triangle. To position this peak correctly, we need to calculate the height, or distance, h of that equilateral triangle. Now we can see the equal segments, which we will call A. Next, we'll establish the formula for A, based on the original line's length, and then calculate h using the formula for the height of an equilateral triangle. First, let's turn on the attribute text overlay. This helps us visualize parameters like the point index numbers directly in the 3D viewport. We start with a curveline node, running from $x equals -0.5 to x equals 0.5. Initially, this line gives us 2 points, with the index numbers 0 and 1. Next, we use the resample curve node and set it to generate 5 points, which divides our single line into 4 equal segments. For some reason, I swapped the start and end values. But that's actually helpful. It clearly shows us that the point index order changes whenever we reverse the start and end direction of the curveline node. Next, I'll introduce the factor feature of the sample curve node, which returns a value from 0 to 1. When we plug the position socket from this node's output into the position of a set position node, changing the factor value will show that single point sliding along the curve's previous location. Now we start setting the position for points with indices 1 and 3. Instead of manually typing 0.3333 into the factor input of the sample curve node, I recommend using a math node. Just take 1 and divide it by 3. This gives us the full, infinite decimal precision we need for better accuracy when the curve gets smaller in later iterations. Next, we set the position for the point with the index number equal to 2. Because we're working within the curve workflow, we can conveniently use the normal vector of the curve with the curve normal node. From the previous resample curve node, we connect a separate node called curve length to retrieve the length value. We now apply the formula established at the beginning of the clip to find A, and subsequently h. With the reverse curve node placed right before the set position node for the point with index 2, we will see the curve's direction get inverted. If you find the content I create valuable, please consider checking out my online store on Superhive Market. Your support is the biggest motivation for me to continue maintaining and growing this channel. You might just find a fantastic 3D product that you need. And now, with every curve line that has 2 points, we want the system to generate the curve segment we've just created. To achieve this, we use the ForEachElement node and set the domain to spline. Next, we prepare the material for the subsequent iterations. What we currently have after the set position node is just one single spline. I want to convert that one spline into 4 separate splines using the following node setup. We can put all these preparation nodes into a group node, and I'll name it prepare_for_loop. Remember to press Tab to easily go in and out of the group node. Now we plug everything we've built inside our ForEachElement node into the repeat zone. With the iteration count gradually increasing, we transform that single curve line into the Coke curve, with each level corresponding to the number of iterations. And for a regular polygon created from the curve circle node, we can extend this same process to create the Coke snowflake. And now we've successfully mastered the Coke fractal using the curve workflow. But how about the mesh workflow? The next section is for those of you who want to dive deeper into the world of geometry nodes. We'll start again with a node that creates a line segment, but this time, it's mesh-based, the meshline node. We can use the exact same value setup for the meshline node as we did before for the curveline node. Before we dive into creating the fractal, I want to introduce the main method for the mesh workflow. First, I'll move the mesh line to a different position using a transform geometry node. As you can see, we have 2 vertices with indices 0 and 1. We use the sample index node to grab the position of those 2 vertices. Then we use those positions and plug them into a mix vector node to set the position of a new point, which we create using the points node. This mixing method is the core principle of this entire mesh workflow. If you found value in this deep dive into geometry nodes, please consider supporting the channel by visiting my store on Superhive Market. My procedural Thorn curve asset offers professional, instant results for projects needing sharp, procedural detail. Thanks for your support. Starting from the original mesh line, we use a subdivide mesh node and set the level to 2. This takes us from the initial 2 vertices to 5 vertices, creating the 4 equal segment lines we need. There is a difference here. Our index order doesn't necessarily run sequentially from 0, left to right, like it did in the curve workflow. But that's not a big problem. Next, I'll set the position for the vertices with indices 2 and 4. Now we set the position for the vertex with the index number equal to 3. We find a vector starting from index number 0 to number 1 on the original mesh line using the subtract vector math node. We then normalize that vector. Finally, we calculate a cross-product vector from that result, using the vector 0, 0, 1 as the second input. Then, using the distance vector math node, we calculate the distance between the vertex with index number 0 and 1. Now we see the complete visual of the Koch fractal curve, level 1. Let's organize these nodes neatly to prepare for the next step. Now, with the for each element node, we select the edge domain. This means every single edge with 2 vertices should now be taken as the input and procedurally generate into the 4 new edges that form a level 1 Koch curve. Again, we put every node inside the for each element node into the repeat zone. With iteration number, we can create different level of Koch fractal from a single edge. To invert the direction of the cross-product vector, we can simply multiply it by -1. We can also create the Koch snowflake by starting with the mesh circle node. So, we've successfully learned how to create the Koch fractal using both the curve workflow and the mesh workflow. Remember to subscribe and I'll see you in the next tutorial.